Hello everyone, I am Lorenzon, professor from Federal University of Pampa, Brazil, and I am here to present the paper that has been developed in collaboration with Antoni Navarro and the researcher Vicenç Beltran from Barcelona Supercomputing Center. Well, many applications from many domains rely on the BLAS libraries in order to exploit the full potential of multi-core systems. Among all the routines available, the general matrix multiplication kernel is a fundamental building block of such applications. Because of that, many libraries provide optimized sequential and parallel versions, such as Intel MKL and AMD AOCL. These high-performance implementations, they are normally implemented using the fork-join execution model. And as far as we know, there is no optimized implementation of the GEMM routine with task-based models. Hence, software developers have the following options. The first one considers that the entire application uses the fork-join model, which is highly optimized for performance. However, it doesn't present malleability, which means that the execution will not be able to deal with intrinsic characteristics of the hardware and the software that may change as the application executes, which will increase the execution time and also the energy consumption. Then, the second option considers that the application is already parallelized with tasks. So, the entire application is parallelized with tasks, and the parallel fork join GEMM kernel is used. In this situation, the outcome will be a very bad performance results due to the oversubscription problems related to the runtime system used to manage the tasks and the runtime systems used to manage the fork join execution. Another situation considers that the sequential GEMM kernel is used instead of the fork-join GEMM kernel. In this case, will be loss of parallelism because the execution of the GEMM kernel will be performed by only one single task, or in this case, the software developer can implement a naive task-based parallel GEMM, which will not be able to exploit the full resources provided to the user. In this situation, this paper proposes an optimized task-based version that can be seamlessly integrated to task-based program. Then, in summary, this paper has the following contributions. The first one is a generic task-based implementation of the GEMM kernel that can be applied to any parallel program interface that provides task-based execution. The second one is two task-based implementations that leverage the advanced features offered by the OMPS2 model. And then we also proposed a heuristic to automatically select the parallelization scheme and the parameters at runtime that optimize the execution time and also the energy consumption when the entire application is executing a GEMM kernel. So here's the agenda for this presentation. First, a brief description of the GEMM kernel and its implementation on the Bliss software framework. Then the task-based implementations proposed in this work are described. We then describe the ASOC, which is the heuristic to automatically select the optimal configurations and parameters for the GEMM kernel. Then the evaluation is presented and followed by the conclusions and future work. The general matrix multiplication kernel can be defined as follows. So there are two input matrices, matrix A and B. And then the multiplication of both matrices is stored in matrix C. So in this work, we have considered the Bliss, which is a software framework that allows the instantiation of high-performance libraries with BLAS functionality. And because also it provides a highly optimized microkernel to implement the GEMM kernel for each microarchitecture. So we do not need to concern about the performance of the microkernel regarding the architecture that the application is running. And also because it considers that all matrices are stored in a row measure order to improve the data locality and also the performance. The Bliss implementation, or the Bliss, provides two different implementations, one sequential and one parallel fork join, highly optimized. The sequential implementation of GEMM kernel by Bliss considers the use of 5 loops around the microkernel. So in the outermost loop, matrix C and B are divided into column panels of size NC, and the matrix A has no changes. In the PC loop, A and the current column panel B are partitioned into columns, and the rows panels of size K, C, respectively. And also in this iteration, Bliss packs the current row panel of B into a contiguous buffer in memory. Then in the third loop, C and the A matrix resultants are partitioned into smaller blocks of MC lines, and also AMC is packed into a contiguous buffer. At this point, to better accommodate data into cache, the JR loop partitions both C and the B resultant matrices into column slivers of width NR, while the innermost loop, IR loop, divides the current block of A into row slivers of height MR. Then the microkernel multiplies the slivers of A by the slivers of B and updates the position on the C matrix. Bliss provides two optimized versions that are implemented using the fork join module, one with OpenP and the other with pthreads. Both of them consider the parallelization of 4 loops around the microkernel, and the loop 4th, which is indexed by PC, is not parallelized. So it is important to highlight here that for each packing of matrix into panels, there is a thread barrier, so only one thread can do it at once. And by the end of the third loop, which is parallelized, there is a thread barrier to synchronize all the threads before moving to the other iteration of the fourth loop. Well, the total number of threads that is going to run the application is defined by the product of the amount of parallelism exploited in each loop. And this number can be tuned by the software developer. So it can define the number of threads for each loop or relies on the Bliss strategy to decide which is the best number of threads for each parallel loop. Let me now present the 3 task-based implementations proposed in this work. We have implemented our 3 task-based versions inside the Bliss sandbox, which is available by Bliss framework in the way that software developers can try different strategies to optimize some of the kernels implemented by Bliss. In these implementations, in order to keep the same structure as the fork join models, we also consider that matrices are located in row measure order. And to ensure that the only difference among the task-based versions and the fork join versions is the parallelization strategy employed, all the algorithms considers the same implementation of the packing for the panels of matrix A and B into contiguous buffers. We have implemented the 3 different versions that I am going to show now. The first one is the generic task-based implementation. Then I will show the OMPS2 Taskloop variant, followed by the Task4 variant. The generic task-based implementation is based on the sequential version that has already been presented in this presentation. It can be implemented with standard OpenP tasks such as the Pragma OMP tasks, and we have chosen to parallelize the third loop around the microkernel, or the IC loop, due to 2 reasons. The first one is that OpenP doesn't provide the wiki dependence features, which is presented in OMPS2, and also due to the amount of parallelism available in this loop. So the parallelization starts by getting the number of CPUs used by the application, which can be either settable by the user via environment variable, or by default it considers the number of cores available in the architecture. Then when the application starts execution, it follows the same structure as the sequential implementation until it gets the Pragma OSS task directive, where a new explicit task is generated from the associated block structured, and at this time each task will receive a different shared block of C. Each color here means a different task, and also a panel of A based on the task ID. All of them will share the same panel P. Here we also define 2 different in-out dependencies, the dependencies on A and the dependencies on C. C is protected so that the positions of the shared matrix are not being updated by more than 1 task at a time. Second, we protected the panel A to ensure that distinct tasks that are created at each PC iteration will run over one after another, sharing the same panel A. It's also worth mentioning that defining these in-out dependencies avoids the need to use a barrier after this loop that we are parallelizing. Then each created task will create its all panels in a private memory. Finally, each created task will compute over a different position of C matrix in parallel, and the OSS task in the end of the execution is used to ensure that all previous tasks have completed the job before returning the C matrix complete to the execution application. In this Taskloop variant, it considers the Taskloop dependencies implemented by the OMPS2. So in the beginning, it starts by getting the parameters that are used by the application to distribute the workload among the tasks that are created, and also the number of CPUs that have already been explained in the generic task implementation. In order to reduce the overhead at the runtime due to the allocation and the allocation of panels at the runtime, this implementation also considers the implementation of the panel allocation before the execution of the kernel itself. Then, when the pragma's task loop directive around the JC loop is reached, each task will be assigned to a different column panel of matrix C and B, and they will share the same matrix A. And here one can observe that the OSS BXX, which is the grain size, is the number of iterations assigned to each task, as one observed here. And the OSS NC is the amount of iterations that each task will perform at each value of JC. So then, in the PC loop, each task will share the same block of matrix A and split the column panel of BJC and KC lines. And moreover, each task packs its column panel of B, PC, into the contiguous buffer B that has already been created. Okay, so when each task reaches the pragma OSS task loop here, it will create different many tasks to parallelize this loop here, these IC loops. And again, to ensure the correct result of the GEMM routine, the algorithm applies the same dependence discussed in the generic implementation. Each created task will again pack matrix A into panels, and from this point on, all tasks will be executed in concurrency in order to execute the microkernel in parallel. In the end of the execution, there is again a pragma OSS task wait to ensure that all tasks have finished the computation before returning the matrix CMN to the program that has called this GEMM kernel. The OMPS2 task4 variant shares the same structure as the Taskloop variant, and the only difference is the use of the for directive and then the chunk size in order to split the number of iterations among the tasks that are created. And in this case, the iteration space is partitioned into chunks, different chunks of size OSS BSI. And in this directive, there is no overhead as the one associated with tasks in dividing the iterations among the tasks. And also there is no need for a specific management or extra allocation, as there is when we are considering the task model only. Furthermore, the synchronization among the tasks in this use of the for variant is handled via data dependencies, not by the use of a task wait directive in this code. Now I'm going to present our heuristic that automatically selects the optimal configurations. Well, given the amount of parameters and implementations that are required to execute with the GEMM kernel, finding the configuration that delivers the best performance and the best energy consumption would require a huge design space exploration, as observed here in this experiment that has been performed on an Intel Xeon processor with 44 cores. And by only considering different configurations of OSS BSX and OSS MC, OSS MC, there are more than 3,000 configurations that has to be exploited in order to have the best one. So given the energy consumption in the y-axis and the performance on the x-axis for the input matrix with the size, and you're running two different variants, Taskloop and Task4, with different parameter configurations, we show here, we highlight here the best configuration for this input set, where each number here means one parameter that has shown here. And the most important here is that if we change the input set, so running the same machine, but only by changing the input set, the configuration that has delivered the best performance and the best energy consumption in the other input set is not the same that delivers the best result in the other input set. So it highlights the importance of having an heuristic to automatically select the optimal configuration to execute the GEMM kernel. So we have proposed the ASOC, which is a heuristic to automatically and transparently select the ideal implementation variant, the Taskloop or the Task4 implementations, and also to correctly select the number of block sizes and iterations that are assigned to each task on each loop parallelized, that are the parameters considered in the implementations. So this heuristic considers the dimensions of the input matrices at hand and also the features of the architectures, which means the number of cores available and the memory hierarchy. We have also integrated it into the Bliss sandbox, so the implementations of the task-based models can leverage this heuristic transparently. So the heuristic starts by first calculating the block size that will be attributed to each task in the 50 loop. Then it calculates the number of iterations that will be assigned to each loop for each task. Then it calculates the total number of tasks that will be created in order to ensure that the total number of tasks will be either a multiple number of cores in order to reduce the load and balancing. Then after getting the number of tasks that will be created in the total, it refines the parameters OSS VSY in order to reduce the load and balancing within the tasks. And by the end, it selects between Taskloop and Task4 when considering if there is work sharing among the tasks or no. So if tasks will share the same structure, Task4 is selected, otherwise Taskloop is selected. So in the evaluation, we have considering different input matrices according to the original paper of the Bliss, which implements the parallel fork join versions. So our 4 cases with different input sets from M and N and K matrices. The experiments were performed on 2 multi-core architectures, one Intel Xeon and one AMD EPYC, able to execute 64 physical threads. And we have considered different configurations. 2 fork join implementations already provided by Bliss with OpenP and pthreads. 2 implementations that consider the generic task-based implementations of GEMM with OpenP and the GEMM with OMS2. 3 optimized versions with the OMS2, one which is the OMS2 task loop variation, and the other which is the OMS2 Task4 variation. Both configurations here consider the best results found by the DSA. Then we also consider the OSS ASOC, which are the results achieved when ASOC is applied. We also consider 2 vendor implementations with of the GEMM kernel, the AMD AOCL, which is the vendor AMD optimized CPU library, and the Intel MKL, which is the vendor Intel library for math kernel library. The performance results are shown considering the raw performance numbers, or are the gigaflops per second, for all input cases. And first, let me explain how the plots are organized. So it considers in the y-axis the performance in gigaflops per second, and it is highlighted the peak performance on each multi-core system. These results here are for the Intel Xeon 44 cores, and each bar here considers one different configuration. So it is the version's average here, the maximum performance activity for each configuration, and the median values for all the values found in all input cases. And here are shown the same results, but for the AMD EPYC 64 cores. It's worth mentioning that the higher are the values, the better is the performance for each configuration. So I start by highlighting here that generic task-based implementations, like the OMP task and the OSS tasks, in both systems are not able to deliver good performance as the other implementations. When one considers the implementation of our OSS ASOC compared to the OpenP highly optimized version fork join provided by Bliss, on the Intel Xeon 44 cores, we are able to provide, on the average, 11% better performance, and when considering the AMD EPYC 64 core, 4% better performance on average than the highly optimized version provided by Bliss. When comparing OSS ASOC with the vendor implementations of the GEMM kernel, the ASOC implementation can deliver competitive results to the vendor implementations, which are highly optimized for that hardware in question. For example, for the Intel Xeon, the Intel MKL library is highly optimized to this hardware. So in this sense, we are only 1.5% distant from the geometric mean of the Intel MKL results. And when considering the AMD results, we are able to deliver 3% better performance than the other vendor implementations. So why does the OSS ASOC heuristic is capable of achieving better performance than OpenP fork join implementation provided by Bliss? The answer is that it provides better use of the hardware resources. As one can observe here, for one configuration that we are showing, the OMP fork join implementation, it has more cache misses than the OSS ASOC implementation. So the lower is better. Then the amount of cache misses impacts the performance and also the energy consumption of the application. Also, when the application is running with the OSS ASOC configuration, the CPUs are better used. As one can observe here, the cycles that CPUs are active is higher in the OSS ASOC implementation than in the OpenP fork join implementation. Now let me consider the energy consumption results. This analysis has been performed on the Intel Xeon processor because we had access to get the energy consumption results from the hardware counters. In this scenario, the energy is normalized to the best result of each input case for all the test cases. It means that the lower the value here, the better is the energy consumption. So it is again shown for all the configurations evaluated in this work. And here we have a zoom in of the results showing that in most cases, the OSS ASOC implementation is capable of beating all the configurations that were evaluated on the energy consumption. So besides providing competitive performance to the Intel MKL vendor, it can also be competitive on the energy consumption, beating most of the proposed implementations that consider the fork join model. Okay, but besides achieving good performance in the energy consumption, what are the benefits of our task-based GEMM kernel? Well, the outcome is the optimization of real-world applications. And to show that, we consider as a use case the Cholesky decomposition. We have implemented different versions of the Cholesky decomposition algorithm, 2 with the traditional task-based parallelization strategy, where each task executes a sequential BLAS kernel. We call it as OMP, which is the OpenP version, plus BLISSEC, and OSS plus BLISSEC with the OMP2 implementation. And we also consider versions that rely on the previous fork join and task-based parallelization strategies. The OpenP plus BLISS OpenP implemented with fork join, OpenP with BLISS implemented with tasks, OSS BLISS with OSS ASOC, and the OSS plus BLISS, OSS DSE, which is the best result found by an exhaustive search. And we have considered the different input sets of the matrix, ranging from 2048 to 65,000 for all the matrices. The experiments were done on the AMD EPIC multi-core architecture. So I show here the raw performance numbers of the Cholesky decomposition use case for each configuration evaluated. So each bar means a different configuration, and the higher the value, the better. So in this plot, it shows the average of all executions in raw numbers, and in this other plot, it shows the normalized performance to the best one on all test cases. Okay, so the first observation is that OSS ASOC delivers better overall performance than the OpenP fork join and task-based versions, as one can observe here in the yellow colors here. Also, OSS ASOC reaches performance levels that are close to the ones achieved by the OSS DSA, which is performed by an exhaustive search, so it has to be performed offline. And more important, OSS ASOC is performed at the runtime and with no previous training phase. But why does the OSS ASOC is better than the other implementations? So the answer is that OSS ASOC delivers better performance because it can exploit all cores during the whole execution. And to show that, to better illustrate the scenario, we have collected some traces that illustrate the benefits of our optimized task-based GEMM kernel. So in this trace, it shows for CPU 0 from CPU 0 to CPU 63, the execution of the Cholesky decomposition, where each color here, each bar, means a different kernel that is running. So the green one is the GEMM kernel, and the purple one are the CIRC and the TRSM kernels. And this is the implementation with the OSS plus BLISSEC, which uses the GEMM sequential version with the task parallel implementation with the program. So when one compares this execution with the execution that considers the entire implementation with tasks, also the program with tasks and the GEMM kernel with tasks, one can observe with this timeline in execution here is that all the CPUs are better occupied. There is no gap between CPUs, which will reduce the execution time of the entire application, providing performance improvements. And this is because the OSS ASOC list can find good configurations for the GEMM kernels, and also that the runtime systems can leverage the additional subtasks created by different BLISS kernels to exploit all cores. Well, in this paper, we have considered and implemented a task-based version of the GEMM kernel that task-based applications can seamlessly leverage to optimize their applications. We have exploited advanced features of OMP2 to minimize the runtime overhead and improve load balancing and data locality. And we have also proposed the heuristic to select the best parallelization scheme and parameters at runtime automatically, with no previous information and no need to notate codes. Our optimized task-based implementation is capable of delivering better performance and reduces energy consumption when compared to the BLISS OpenP highly optimized fork join implementation, and also when compared to Intel MKL and AMD AOCL versions of the GEMM. It has also been shown that real applications can enhance their performance by leveraging our optimized task-based implementation. As feature work, we intend to implement the optimized task-based versions of other linear algebra routines. Well, this work has been supported by the AGPC 3 Europa, which is an AGPC European project, and also by the FAPERGS funding agents from Brazil. So I am able to questions, and thank you for your attention. Please, if you have any question or comments, just send me an email and I will be prompt to answer you. Thank you very much.